So in this video, we will be designing a universal shift register, where a universal shift register basically loads data in parallel and perform a shift in either direction, either right or left. And in this case, there are 4 operations. We have our load, shift right, shift left, and pause. We also use a control signal to specify the direction either to move right or to move left. So with the right shift register, where we will be shifting right, we are going to have our output Q as initially 0, 0, 0. Then we're going to shift 1, which is going to be our input. We're going to shift it right this way. That's when our control here is set to shift right. When we set our control to shift left, then we will be shifting 1, which is from the input. We will be shifting it to the left, and this is going to be the sequence of our output Q. So now I'll move on to writing the code, and then I will explain after. So just open up your favorite text editor, and then we create our So as we initially said, we have clock, reset, and control, and then our input as our inputs, and then we have Q as the output. So we basically declare our outputs here, and then our signals, which are these signals R next and R next and R register, and then we move on to, as usual, dividing our circuit into 3 different parts, where we have our registers, which are the D flip-flops, and then we have our next state logic, and we have our output logic. it's all centered on this particular register. So we write our register process like this, which has asynchronous reset, and it's good practice. Your register should always be active low, so that in a circuit, if you in a real circuit, if your power goes below a certain point, then your circuit resets, which is what it's supposed to do. So since our signal is a vector, instead of writing all zeros, we simply say this is how you write others equals to zeros. And on a rising edge, we have our next state becoming our current state. And then we move on to our next state logic. And in here, our primary component is this particular max. And based on this, we are passing our current state to our next state register, where we to our next state of the register. And so our rnext, we simply pass it when we have our pause. When you have pause, we pass the same signal. You can consider this as an enable. And so when it's 0 0, we simply pass we keep our previous signal, our previous output. However, when we have 0 1, then we shift left, where we basically take the initial, we basically take the less significant bit of our register and of our output, and we shift it left. So, and when we have shift right, which is at 1 0, we take our LSB, we take our MSB, which is our most significant bit of our output, of our input D, and shift it to the right. And when we have 1 1, then we are on the load stage, where we are loading our input. Great. So now let's write our test bench so that we will be able to test our signal. To do this, I'm going to first of all create our universal shift register test bench. And then I'm going to go through the process of, I'm going to write the code and then I will explain. So this is the test bench, and in the test bench, we basically declare our signals. This is for our clock period where we set it to 1 microsecond. And so we declare our signals as the ones in the input, as the ones in our system, in our universal shift register here that we designed. And then after that, we have our unit under tests, which is our universal shift register that we designed. And this is our clock process. With a stop condition to help us stop. And so we start by resetting our system, where we should actually reset 1. We wait for this amount of time, 2 clock cycles, and we are actually supposed now to have our reset become 0. Now our system has been set, and reset now is 0. Actually, as we designed here, we said that our reset is active high. So our reset should actually be active low, such that if our reset is 0, then our system goes to reset, which is what you want if your power goes below. So we say that we reset our system, and then we unreset it. Then we have our input. We load our input. Our control is we have our control like this, which is where we actually load our input data. Then we wait for 2 clock cycles, and we have control. We change our control to 0, 1, which will allow us to shift left, and then wait for 4 clock cycles. So we expect then our output to be 1, 1, 1 at this point, as we are shifting to the right. We're shifting this one to the right, and then we load another input, with 1 being the MSP this time, where we're supposed to observe, and we set our control to 1, 1, 1, which means, okay, here we'll be loading our new data, and then we wait for 2 clock cycles. We set our control to 1, 0, which will be shifting to the right, and we have a control signal. This one is for the pause, where after we shift, then we can pause where we don't have, where our input will remain, where our output will remain constant, even though we have our clock cycle running. And then finally we end our simulation. So we are now going to run this in Xilinx, and let's see how the results will be. So we're going to run it in Vivado. So now let's say, let's run our simulation. And as you can observe here, let's observe our control, where we start with 1, 1, and we say that we are loading, this is our day, this is our output. First, when we do our reset, which is active low, in this case our output becomes 0, and then we load, which is 1, 1, and our output becomes 1. So let me just make this into this is in binary, so our output is 1, and let's see if we can change this to binary. Yes, okay. So here now we start shifting. We say we input this one, and then we start shifting to the right as we start shifting to the left as our control says here. And as we said, our control is we shift left when we have 0, 1 for control, so that is 1, and we can change this. So when we have 0, 1 in control, we are shifting it to the right, and we're still shifting it to the left, so we can see that our 1 is being shifted to the left, so forth until our 4th clock cycle, where we have all of it shifted to the left. And then we say again, we load, where we say 1, 1 as control, and we load, this time we load 1, 0, 0, and then we start shifting it, and then we set our control to 1, 0, which is shift to the right. And as you can see, we have 1, 1, we have the 1 shifted to the right, like that, until the 4th clock cycle, where we have all of it as 1, 1. And then we set our control to 0, where we have the pause, and we can see that our output is unchanged until we have until now we have a reset low until our simulation ends. So it seems that our circuit is working as we expected, and yeah, that's it for the universal shift register, where you can either shift right or shift left using the control signal. So thank you for listening. I hope you've been able to learn something. See you in the next video.